I want to ask you to imagine traveling at the speed of light, not approaching it, not getting close, actually traveling at exactly c 299,792,458 meters per second, the exact speed of light through vacuum. What would you experience? The answer, when you work it out carefully from the mathematics of special relativity, is extraordinary and deeply strange. At the speed of light, time does not slow down. Time does not tick more slowly. Time stops entirely. Not for the rest of the universe, for you. At exactly c, no time passes for the traveler at all. The emission of the journey and the arrival at the destination are the same event. There is no duration, there is no before and after, there is just here and there simultaneously. This is not a figure of speech. It is a precise mathematical result derived from the Lorentz transformation, the core mathematical machinery of special relativity. And it has consequences that are among the most counterintuitive in all of physics, including implications for what it means to exist in time, what the photon experiences, if it experiences anything, and why the structure of space-time is exactly the way it is. But I want to start with a caution. The phrase traveling at the speed of light contains a hidden assumption that is physically impossible for any massive object. You cannot actually travel at exactly c if you have mass. The reason is also a consequence of special relativity, and I want to explain it carefully before we discuss what happens at c. Because the impossibility is not a technicality. It is a window into what time and space actually are. Let me begin with the Lorentz transformation and what it says about time dilation at arbitrary velocities. Special relativity is built on two postulates. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is the same for all inertial observers, regardless of the motion of the source or the observer. From these two postulates, Einstein derived the Lorentz transformation in 1905. The Lorentz transformation describes how the coordinates of an event, its time and position, transform between two reference frames moving at constant velocity v relative to each other. If one frame assigns coordinates t, x to an event, the other frame, moving at velocity v along the x direction, assigns coordinates t prime, x prime, given by t prime equals gamma times t minus v times x divided by c squared, x prime equals gamma times x minus v times t, where gamma equals 1 divided by the square root of 1 minus v squared over c squared. The gamma factor is the key to everything. At v equals 0, gamma equals 1, and the coordinates are unchanged. As v increases towards c, v squared over c squared approaches 1, 1 minus v squared over c squared approaches 0, and gamma approaches infinity. The time dilation formula follows directly. Consider a clock at rest in the moving frame, sitting at a fixed position x prime equals 0. In the moving frame, two events on the clock's world line are separated by a time interval delta t prime. In the stationary frame, the same two events are separated by a time interval delta t equals gamma times delta t prime. Since gamma is greater than 1, delta t is greater than delta t prime. The moving clock's ticks, as measured in the stationary frame, are spaced further apart. The moving clock runs slow. This is time dilation. A moving clock runs slow by the factor gamma. At 10% of c, gamma is approximately 1.005, and the clock runs slow by 0.5%. At 90% of c, gamma is approximately 2.3, and the clock runs at approximately 43% of its stationary rate. At 99% of c, gamma is approximately 7, and the clock runs at approximately 14% of its stationary rate. At 99.9% of c, gamma is approximately 22, and the clock runs at about 4.5% of its stationary rate. As v approaches c, gamma approaches infinity, and the clock rate approaches 0. At exactly v equals c, the formula gives gamma equals infinity, and the clock rate equals 0 divided by infinity, which is 0. The clock stops. Let me be more precise about what this means. Because the formula for gamma diverges at v equals c, and infinity times 0 is mathematically indeterminate, the correct way to express the result is through the proper time, the time measured by the clock itself. The proper time elapsed along a world line between two events is tau equals the integral along the world line of the square root of 1 minus v squared over c squared times dt. This is the time experienced by a traveler, the time measured by a clock traveling with the object. For a massive object moving at constant velocity v from event A to event B, the proper time is tau equals t divided by gamma, where t is the time elapsed in the stationary frame. As v approaches c and gamma approaches infinity, the proper time tau approaches 0. In the limit v equals c, tau equals 0, no time elapses for the traveler. For a massless particle like a photon, the world line is a null geodesic. The space-time interval along the world line is 0. The proper time for any segment of a null geodesic is exactly 0. Not approximately 0, not very small, but positive. Exactly 0. A photon emitted anywhere in the universe and absorbed anywhere else in the universe has 0 proper time elapsed between emission and absorption, regardless of how far the photon has traveled as measured in any other frame. This is the precise content of the statement that time stops at the speed of light. It means the proper time, the time experienced by the light speed traveler, is exactly 0. The emission and absorption events are separated by 0 elapsed proper time. For the photon, in the most literal mathematical sense allowed by the theory, there is no time between being created and being destroyed. If this is already fundamentally changing how you think about time and existence, the principles I have collected for understanding the fabric of reality include exactly this: how the nature of time reveals the structure of what it means to exist. Ready to change how you see the world? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Now let me address the impossibility for massive objects, because this is as important as the result for massless particles. Why can a massive object not reach the speed of light? The answer is in the energy required. To accelerate a massive object to velocity v requires energy equal to m times c squared times the quantity gamma minus 1. As v approaches c, gamma approaches infinity, and the required energy approaches infinity. No finite amount of energy can accelerate a massive object to exactly c. This is not just a practical limitation, it is a theoretical one. No matter how much energy you have available, you can never reach exactly c with a massive object. You can always get closer. You can reach 99.99999% of c, or 99.9999999%, but the last decimal place can never be filled in. The velocity c is an asymptote. You can approach it indefinitely but never reach it. The deeper reason is in the structure of the Lorentz transformation. At v equals c, the time transformation becomes t prime equals infinity times 0, which is indeterminate. The transformation breaks down. There is no consistent Lorentz frame for a massive object moving at exactly c because the coordinate system collapses, the time axis and the space axis are tilted together into the same direction, leaving no distinction between space and time. This is the geometric picture I want to develop because it is more illuminating than the energy argument. In the space-time diagram, the world line of a massive object at rest is a vertical line, all time, no space. The world line of a massive object moving at velocity v is a line tilted from vertical by an angle whose tangent is v over c. As v increases, the world line tilts more toward the horizontal. The world line of a massless particle is a line at exactly 45 degrees from vertical, the light cone. A Lorentz transformation is a hyperbolic rotation of the space-time coordinate system. It tilts the time axis and the space axis toward each other in a way that preserves the light cone. The time axis can be tilted by any amount by choosing a reference frame moving at the appropriate velocity. But the time axis can never be tilted past the light cone by any physical Lorentz transformation. Why not? Because the light cone is the boundary between the causal future and the causal past on one side and the space-like region on the other. Tilting the time axis past the light cone would mix the causal future with the causal past, converting time-like separations into space-like ones. This would reverse the time ordering of causally connected events, violating causality. The impossibility of a massive object reaching C is therefore a causality requirement. If massive objects could reach C, a Lorentz transformation would exist that reversed the time ordering of any event on the massive object's world line. This would lead to causal paradoxes and would make the physical laws inconsistent. The impossibility of massive objects reaching C is not a dynamical constraint that could in principle be overcome with more energy. It is a logical requirement of consistent causal structure. Now let me develop what it actually means for time to stop at C, because I think the popular accounts are often misleading in two opposite directions. The first misleading direction is to say that time stopping at C is an observer-dependent statement. It is time in the photon's frame, which is not a well-defined frame for a massless particle. The photon, having no rest frame, has no experience of time in the same way a massive particle does. The statement that time stops for the photon is therefore not about the photon's subjective experience, but about the zero proper time along its null geodesic. This is correct and important. But it does not diminish the physical significance of the zero proper time. The proper time is not a coordinate or a convention. It is an invariant. All observers agree on the proper time elapsed along a given world line. The zero proper time of a photon's journey from the Andromeda Galaxy to Earth is agreed on by every observer. No observer, regardless of their motion, computes a non-zero proper time for the photon's journey. The second misleading direction is to conclude that the photon therefore exists in a special timeless state, experiencing emission and absorption simultaneously in some cosmic sense. This anthropomorphizes the photon in a way that goes beyond the physics. The proper time of a null geodesic is zero. This is a mathematical statement about the space-time geometry, not a statement about the photon's consciousness or experience. What the zero proper time means physically is this. The photon's world line has zero length in the Minkowski metric. Two events connected by a null geodesic, an emission event and an absorption event, have zero space-time interval between them. They are as close as two distinct events can be in space-time, in the sense that the invariant space-time distance between them is zero. This has a specific and important implication for the concept of the photon's identity. A massive particle can be tracked through time. At time t1, it is here. At time t2, it is there. And it is the same particle throughout, because there is a continuous time-like world line connecting its earlier and later states. The continuity of the world line, parameterized by proper time, is what makes the particle the same particle throughout its history. A photon with zero proper time along its world line cannot be parameterized by proper time in the same way. The world line exists as a geometric object in spacetime, connecting the emission event to the absorption event. But the parametrization of this world line by an affine parameter, the photon equivalent of proper time, is not proper time itself. The affine parameter along a null geodesic increases from emission to absorption, but it is not a measure of elapsed time in the same sense. Whether a photon is the same photon throughout its journey is a question that requires careful thought. In quantum electrodynamics, the photon is treated as a quantum excitation of the electromagnetic field. The emission event creates the excitation, and the absorption event destroys it. Whether there is a sense in which the photon that is absorbed is the same photon that was emitted, or whether this question is even well posed, depends on the interpretation of quantum mechanics that you adopt. What we are exploring is one of the deepest questions in physics. What does it mean for something to exist through time? The principles I have found most useful for thinking about this, for connecting the mathematics of space-time to the experience of existence, are in my book. Get 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me now develop the twin paradox, because it is the clearest demonstration of time dilation and proper time in action, and it directly illustrates what the zero proper time of a null geodesic means in contrast to the finite proper time of massive particle world lines. The twin paradox is the following. Two twins are at the same location. One stays on Earth. The other travels to a distant star at high velocity and returns. When the traveling twin returns, they are younger than the stay-at-home twin. This is not a paradox in the sense of a contradiction. It is a paradox only in the colloquial sense of being surprising. The result is a straightforward prediction of special relativity confirmed experimentally by the Hoffele-Keating experiment and by particle physics experiments every day. The mathematical statement is simple. The proper time along the traveling twin's world line, calculated by integrating the square root of 1 minus v squared over c squared along the world line, is less than the proper time along the stay-at-home twin's world line, which is simply the coordinate time elapsed in the Earth frame. The stay-at-home twin has a straight world line in space-time, vertical, purely temporal, no spatial component. The traveling twin has a curved world line. It goes out to the distant star and comes back, making a bent path in space-time. The straight world line has the maximum proper time between the two endpoints. The bent world line has a shorter proper time. This is the geometric content of the twin paradox. The geometric result is analogous to the triangle inequality in Euclidean space, but with a crucial sign difference. In Euclidean space, the straight path between 2 points is the shortest path. Any detour through space adds length. In Minkowski spacetime, the straight path between two events is the longest path. Any detour through space subtracts proper time. This is because of the minus sign in the Minkowski metric. The traveler who takes a spatial detour ages less. Specific numbers make this concrete. A spacecraft traveling at 99% of c to a star 4.24 light years away, Proxima Centauri, takes approximately 4.3 years in Earth frame time for the one-way journey. The spacecraft's gamma is approximately 7. The crew ages approximately 4.3 divided by 7, or approximately 0.61 years, less than 8 months during the 3-year Earth frame journey. If they turn around immediately and return at the same speed, the stay-at-home twin has aged approximately 6 years, and the traveling twin has aged approximately 1.2 years. The difference is 7.4 years. At 99.9% of c, gamma is approximately 22. The one-way journey in Earth frame is still approximately 4.3 years. The crew ages approximately 4.3 divided by 22, or approximately 0.2 years, about 2.4 months, The round trip leaves the traveling twin younger by approximately 8.3 years relative to the stay-at-home twin. At 99.9999% of C, gamma is approximately 707. The crew ages approximately 4.3 divided by 707, or approximately 0.006 years, about 2 days during the 4-3-year Earth frame journey. The round trip makes the traveling twin younger by approximately 8.59 years relative to the stay-at-home twin, who is aged 8.6 years. The limiting case is a photon. A photon making the round trip at exactly C would complete it in exactly 48 years in Earth frame time, but with 0 proper time elapsed, the photon arrives back having experienced no time at all. Of course, a round-trip photon requires something to reflect it at Proxima Centauri. In practice, this is the travel time of a radar signal. The twin paradox has been tested experimentally. In the Hoffele-Keating experiment of 1971 cesium, atomic clocks were flown around the world on commercial aircraft and compared to identical clocks left at the United States Naval Observatory in Washington, D.C. The moving clocks ran slower than the stationary clocks by amounts consistent with special relativistic time dilation plus a general relativistic correction for the altitude of the aircraft. The special relativistic time dilation was confirmed to within the experimental uncertainties. More dramatically, particle accelerators test time dilation continuously. Unstable particles produced in accelerators live longer in the lab frame than their rest frame lifetime by the factor gamma. Pions produced in cosmic ray interactions in the upper atmosphere have rest frame lifetimes of approximately 26 nanoseconds. But pions produced at 99.9% of C have gamma of approximately 22, making their lab frame lifetime approximately 570 nanoseconds. They travel approximately 170 meters before decaying, rather than the 7.8 meters they would travel if time dilation did not apply. Time dilation for pions and muons at particle accelerators has been measured with extraordinary precision, confirming the Lorentz formula to many decimal places. The twin paradox is not a thought experiment. It is an observed, measured, confirmed physical fact. Particle accelerators are experimental demonstrations of the twin paradox running continuously. Now let me connect the twin paradox to the speed of light limit. The traveling twins' proper time is reduced by their speed. The faster they travel, the less they age during the journey. At the extreme limit, a traveler moving at exactly C would have 0 proper time. They would age not at all during the journey. They would arrive at the distant star at exactly the same age as they left Earth, not just younger, but with 0 elapsed time. This is the precise physical content of time stopping at the speed of light. It is the V equals C limit of the twin paradox. As V approaches C, the traveling twin ages less and less relative to the stay-at-home twin. In the limit V equals C, the traveling twin ages not at all. A photon emitted from Earth toward the Andromeda Galaxy arrives there after 2.537 million years of Earth time, but after 0 proper time for the photon. The universe has aged 2.537 million years. The photon has not aged at all. Now let me extend this to general relativity. Because time dilation also occurs in gravitational fields, and the connection between gravitational time dilation and the speed of light limit reveals something deep about the relationship between gravity and space-time geometry. In general relativity, time runs at different rates at different points in a gravitational field. Clocks at higher gravitational potential run faster than clocks at lower potential. At the surface of Earth, clocks run approximately 1 part in 10 to the 9th slower than clocks far from any gravitational field. At the surface of a neutron star, clocks run approximately 70% of the rate of clocks far away. At the event horizon of a black hole, from the perspective of an external observer, clocks stop entirely. This is the gravitational version of time stopping at the speed of light. As a falling observer approaches the event horizon, the gravitational time dilation becomes arbitrarily large from the perspective of a distant observer. The falling observer's clock, as seen from outside, appears to slow down, tick more and more slowly, and asymptotically freeze at the horizon. From the falling observer's own perspective, their clock continues to tick normally. They cross the horizon in finite proper time and continue toward the singularity. The external observer never sees them cross the horizon. The internal observer crosses it without any local difficulty. The connection between the black hole horizon and the speed of light limit is precise. At the event horizon, the escape velocity equals c. Locally, at the horizon, the space is being swept inward at the speed of light. An outward moving photon at the event horizon is exactly stationary in the coordinates of the distant observer. It is moving at c outward through space, but the space is moving at c inward, so the net motion is zero. Light is frozen at the event horizon. Time stops at the event horizon from the external perspective for exactly the same reason that time stops at c in special relativity. The speed of light is the boundary between the causal future and the causal past, and at c, no new causal connections can be made. The gravitational time dilation and the kinematic time dilation of special relativity are unified in general relativity through the equivalence principle. The local effects of gravity are equivalent to the local effects of acceleration. An accelerating rocket in flat spacetime experiences exactly the same time dilation as a stationary observer in a gravitational field of the same strength. The two types of time dilation, gravitational and kinematic, are aspects of the same underlying space-time geometry. The fact that time stops at the horizon of a black hole and at the speed of light for the same geometric reason is one of the most profound unifications in physics. Seeing these connections, finding the principles that unify apparently disparate phenomena is exactly what my book is about. Ready to change how you see the world. Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now address what I think is the most philosophically important question raised by the fact that time stops at the speed of light. What does it mean for the photon to exist? I want to approach this carefully because the question touches on deep issues about the nature of time, personal identity, and existence. And I want to be precise about what we can and cannot say from the physics alone. In ordinary experience, existence through time means continuity. You are the same person you were yesterday because there is a continuous thread of memory, physical continuity, and causal connection from your past self to your present self. The passage of time is the medium in which this continuity unfolds. Without time, existence as we understand it seems impossible. A photon with zero proper time along its null geodesic does not exist through time in this sense. There is no continuous thread of development from the photon's emission to its absorption. The two events are the same event from the photon's geometric perspective. Zero proper time separates them. The photon does not grow, change, develop, or experience anything during its journey, not because nothing happens to it, but because there is no time in which anything could happen. The photon exists in space-time as a geometric object, a null geodesic connecting two events. But it does not exist through time in the way that massive objects exist through time. Let me contrast this with the existence of a massive particle to make the distinction clear. Consider an electron emitted by an atom in the Andromeda Galaxy. The electron has non-zero mass. Its world line is time-like. In the Andromeda Galaxy's rest frame, the electron exists from the moment of emission for as long as it takes to be absorbed or to decay into other particles. During this time, the electron accumulates proper time. It has a before and an after. It has a temporal history. The photon emitted at the same event in Andromeda has a null world line. In the same frame, it was emitted approximately 2.537 million years ago and arrives at Earth tonight. From Earth's perspective, the photon has been traveling for 2.537 million years. But along the photon's own null geodesic, zero proper time has elapsed. The photon has no before and after in the temporal sense. It has no temporal history. Now here is the question that I want to sit with. In what sense is the photon arriving at Earth the same photon that was emitted in Andromeda? For massive particles, the answer is clear. The same particle is the one with a continuous time-like world line connecting the two events. The particle persists through time, accumulating proper time, and its identity is maintained by the continuity of this world line. For the photon, the world line exists as a geometric object in space-time, but there is no proper time parameterizing it in the usual sense. The photon does not persist through time in the massive particle sense. In quantum electrodynamics, the photon is treated as a quantum excitation of the electromagnetic field. The emission event creates the excitation, and the absorption event destroys it. Whether there is a sense in which the photon at absorption is the same photon as at emission depends on whether you require temporal continuity for identity. In the block universe picture, the photon's null geodesic simply exists as a geometric feature of the space-time block connecting the emission event to the absorption event. The photon is present at both events as a feature of the space-time geometry. Whether it is the same photon at both events, or whether asking this question is even meaningful, is a question about the nature of identity in a timeless block universe that does not have a clean answer in standard physics. What is clear is that the photon carries information and energy from the emission event to the absorption event. The information is preserved along the null geodesic. The same quantum state arrives at the detector as was emitted at the source, modulo any interactions along the way. The energy is preserved. The phase of the electromagnetic wave is preserved. In these physical senses, it is the same photon. In the temporal sense, whether the photon is the same at two events, separated by zero proper time, whether there is a fact of the matter about its continuous identity through its journey, is a question where the physics gives us the mathematical framework but not a definitive philosophical answer. Let me now address what I think is the most important thing to understand about time stopping at the speed of light, which is what it reveals about the nature of time itself. Time, as we experience it, is a local phenomenon. It is the proper time accumulated along a specific world line. Different world lines accumulate different amounts of proper time between the same two events. The world line of maximum proper time between two events is the geodesic, the straightest possible path corresponding to an observer at rest relative to the endpoints. Every deviation from the geodesic, every detour through space, reduces the proper time. As the deviation increases, the proper time decreases towards zero. At the extreme limit, a null geodesic has zero proper time. The progression from maximum proper time to zero proper time as velocity increases from 0 to c is the progression from deepest temporal existence to no temporal existence. We inhabit a universe in which time exists because we are massive objects moving through space-time at velocities well below c. Our proper time is always positive. Our world lines are always time-like. We always have a before and after. We always age. We always experience time passing. But we inhabit a universe where massless particles, the photons that carry information and light, have no temporal existence whatsoever. They connect events across the universe in zero proper time. They do not age. They have no history. They simply are at the boundary between here and there, between then and now, between existence and non-existence in time. Time stops at the speed of light because light is the carrier of the causal structure, and the causal structure is what time is made of. At sea, all of the journey is spatial and none is temporal. The universe has arranged itself so that the particle that carries causality itself stands outside of causal time. From the question of why time stops at the speed of light, we arrive at something profound about the nature of time itself, that it is a local, observer-dependent, proper time phenomenon that emerges from the structure of space-time. These are the kinds of principles that transform how you think about everything. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What from today's video changed how you think about time? Tell me in the comments. If this changed how you think about time and its relationship to the speed of light, if the zero proper time of a photon's null geodesic reveals something about the nature of temporal existence that you had not considered, tell me in the comments. Tell me whether you find the geometric picture of the light cone as the boundary of causal time more or less illuminating than the energy argument for why massive objects cannot reach C. Tell me whether the comparison between time stopping at the speed of light and time stopping at the event horizon of a black hole, two phenomena arising from the same geometric reason, changes how you think about the relationship between special and general relativity. And subscribe if you want to keep going into the places where the most fundamental questions about the nature of time and existence meet the most precise physics we have for answering them.